All right. So let me recall what I was doing yesterday. So just a brief recap. So I was considering the sub-Riemannian, or called the Sire-Yamabe problem, or the Webster-Yamabe problem. The structure of the PDE is completely similar. So we're in 3 dimensions. Okay, so this is on M3, J, and theta. And we have a so-called sub-elliptic operator. So the structure of the equation is completely analogous to the Yamabe equation. But here, so there are 2 differences. Here, instead of the Laplacian, we have the sub-Laplacian. So essentially, it's the Laplacian only in the contact distribution. And this exponent here is like the Riemannian exponent in 1 more dimension. Okay, because we have this, we have a sort of lack of isotropy. So for any point of the manifold, we have a 2-dimensional distribution, which changes with the point. And we're taking the Laplacian only in that direction. And if we consider this distorted distance given by the distribution, then there is a change in the homogeneity of the space. So a 3-dimensional space behaves like a 4-dimensional space. And that's why here we have the Sobolev exponent, like in the Riemannian 4D case. All right, so I described a parallel between the Riemannian-Yamabe problem and the sub-Riemannian-Yamabe problem. So everything is very similar if we are in high dimension. So if we are in a topological dimension greater or equal to 5, okay? But there are some differences in dimension 3. So when this little n is 1. And I was discussing a sort of positive mass theorem because you would like to understand the Green's function of the operator that appears in order to expand the Yamabe quotient. In high dimension, it's a local quantity that determines the expansion. In low dimension, it's a global object, and it has to do with the expansion of the Green's function. Okay, so we have an expansion of the Green's function just as in the Riemannian case, but in 1 more dimension. And I discussed the positive mass theorem we have. So we have the positivity of this constant A, so it's like a positive mass theorem, but we assume the manifold to be embeddable, okay? So embeddable means that there is a map from the manifold into some Cn, okay? So this dimension n can be anything, okay? Such that you sort of pull back the complex structure from Cn to the contact spaces. Okay, so we have this result in 3 dimensions, assuming the manifold is embeddable. All right. Maybe I'll just say a few words about the proof. And I recall that as a corollary, we know that the infimum of the Yamabe quotient on a manifold is lower than the spherical one, and it is attained. And as a consequence, the sub-Riemannian Yamabe problem is solvable. Okay, so let me copy the theorem. So the proof is sort of, I mean, I won't say much, but the proof is inspired by some work by Witten in '86. So he proved, So Witten proved the positive mass theorem on spin manifolds. Okay, so here's the spinors. I don't have time to introduce them, but he wrote a mass formula in terms of some spinor, which was solving the Dirac equation on the manifold. Okay, so essentially, it uses some tricky integration by parts. And so we have to say that, okay, we don't prove exactly, so our statement was assuming indeed that some operator that I call P to be positive definite, okay, instead of embeddability. So here P is the so-called CR Penn's operator. Let me call it P theta. So this Penn's operator is a fourth order operator. And writes as essentially the sub-Laplacian squared plus some lower order terms. And the nice thing about this operator is that it is conformally covariant. In the sense that if you change, say, theta hat to u squared times theta, then the Penn's operator with respect to theta hat is equal to u to the minus 4 times p theta. Okay, so we proved the positivity of the mass, assuming that this Penn's operator is greater or equal to 0. But then there was a paper by Takeuchi from 2020. So he proved that if the manifold is embeddable, then the Penn's operator is actually non-negative. Okay, and therefore I prefer to state the theorem in terms of embeddability rather than in terms of the positivity of this operator, which is a bit mysterious. So it enters nicely in some formula with integration by parts, but the condition of embeddability is way more clear. Oh, by the way, I should mention that so in this integration by parts, we relied heavily on some work basically made on purpose by Xiao and Jung. From 2015. Okay, it's some work in micro-local analysis which allowed to solve some PDE, which has to do with the Dirac equation by Witten. Okay, so I should acknowledge that. Okay, so the catch is that, okay, so if we are in dimension greater or equal to 5, So by a result by Boutet-de-Monvel, which I mentioned yesterday. So if n is greater or equal to 2, so if we are in topological dimension greater or equal to 5, okay, then M is embeddable. But it's not always true, actually, embeddability. Is, say, rare in, say, for three-dimensional structures. Okay, and we saw that if M3J theta is embeddable, then we have the positive mass theorem. And the positive mass theorem in turn implies that the Yamabe, the Sire-Yamabe constant is attained. Okay, so today I would like to show that in fact, this assumption is indeed crucial. Okay, so we have examples, we have counterexamples in which this fails, and this also fails. Okay, so this is very different from the Riemannian case. Okay, so I want to say that this embeddability assumption is indeed crucial. All right, so let me discuss some counterexamples. Okay, so there are these so-called Rossi spheres. So this was constructed by Hugo Rossi in 65. Rossi is the most common last name in Italy, but actually this guy, Hugo Rossi, was from Argentina. Okay, probably from Italian background, but yeah, he was Argentinian. Okay, so these are examples of non-embeddable manifolds. Okay, so we saw that by the result by Boutin and Monvel, manifolds are always embeddable if the topological dimension is greater or equal than 5, but in 3 dimensions, it's not always true. But these Rossi spheres are quite simple because they are homogeneous spaces. So basically, you don't distinguish one point from the other. And they're just constructed from the standard sphere. So recall that the standard sphere, okay, it's one of the examples that we discussed yesterday. So we have S3, which is contained in C2. And I use ambient coordinates Z1 and Z2. And understanding J means to understand the I eigenvector of J. And for the round sphere, so for the standard sphere, we have that Z1. So this is the canonical. Okay, canonical. Is z2 bar dz1 minus z1 bar dz2. Okay, and the canonical rotation of S3. Okay, so this is the canonical. Is the one sending z1 S3 into I times z1 S3. Okay, so Ross spheres, and by the way, z1 S3 determines the contact distribution Xi S3. Okay, so Ross spheres have the same, have the same, say, Xi S3 with the contact form theta S3, but JS is, so here S is a real number, is such that JS of Z1S is equal to I Z1S. Okay, and Z1S is Z1 S3 plus S times the conjugate bar. Okay, so this is the conjugate. Okay, so this is a distortion of the complex rotation of S3. Okay, it's a different one. The contact plane is the same, but the complex rotation J is different. Okay, and it's determined by a change of the eigenvector. Okay, so notice that J0 coincides with the standard rotation of S3. Sorry, J0. Okay, but otherwise, so if you take S to be non-zero, then the complex rotation is a little different. Okay, so these are actually homogeneous. So for, okay, they're homogeneous. So with respect to the SU2 action, in C2. Okay, so if you apply a map, a linear map in SU2 in C2, then the Ross spheres are actually, they stay the same, okay? But they are non-embeddable if S is different from 0. Of course, they are embeddable when S is 0 because you have just a standard sphere, which inherits the complex structure on the contact plane from C2. Okay, but not when S is different from 0. So you keep the same contact plane and the same contact form. So theta 0 is I over 2 sum for j running from 1 to 2 of zj dzj bar minus zj bar dzj Okay, so this is stays the same for all values of S. Okay, so maybe let me recall some formulas here. Okay, so the theorem we have is the following. So theorem D. So this is due to Cheng, myself, and Paul Yang from 23. Is that for any P in S3, JS theta 0. And but actually, I said all the points are equivalent. Okay, so you can just fix any point you like. So for any point and for absolute value of S small, non-zero, the mass AS in the expansion of GB. Okay, so this is the Green's function of the conformal sublaplacian, satisfies AS equal to minus 18 pi S squared plus little o of S squared. Okay, so notice that it is negative for S non-zero. Okay, so we have a manifold with positive, say, scalar curvature, but a counterexample to the positive mass theorem. And this is due in sub-Riemannian geometry to the non-embeddability of the structure. Maybe I can just say a few words about the proof. So uses some matched asymptotics of so for the expansion just a second. Of say GB S. So we need to study. So this is the conformal sublaplacian on Rosse sphere applied to the Green's function S. So we want to solve right-hand side with the Dirac delta. Okay, so in say spatial coordinates, near P. So I discussed the conformal normal coordinates in the Riemannian case. So this is a set of coordinates which is sort of equivalent. Okay, so you need to choose the local coordinates very carefully to be able to expand the Green's function, so GBS in this way. So 1 over rho S squared. So this is the homogeneous distance. plus AS plus a big O of rho S. On the other hand, so you have one local expansion in this way. Now the point is that, okay, you need to work to write down those coordinates, but they are explicit. But if you use this set of coordinates, then this AS, you cannot tell because it's a global object. Okay. On the other hand, you can use, ambient coordinates in C2 to Taylor expand in S GS, GBS in S. Okay, so the point is that if you use the ambient coordinates, then this can become explicit. So GBS becomes GB0 plus S GB1 plus S squared GB2 and so on. Okay, so the GBI are explicit. Okay, but the catch is that the ambient coordinates in C2 are not good coordinates to be able to write this expansion. Okay, so everything is sort of screwed up because the good coordinates are those normal coordinates near the point P, and the ambient coordinates have nothing to do with it. Okay, so we get two separate expansions, one in a set of good coordinates, but you don't know the next order term because it's a global thing. The other is to use the ambient coordinates, so the wrong coordinates, to get an explicit expansion, and then we have to match the two. Okay, so we have to do matched asymptotics. Okay, so it was like a painful, agonizing work about trying to match the two expansions in two different sets of coordinates. Okay, so the choice of local coordinates is especially very, very complicated. And for the Taylor expansion, you can essentially guess. Okay, so we used some mathematical software to guess some explicit solutions in the ambient coordinates. Is there any question? Okay, so this was a counterexample to this. So we saw that if the manifold is embeddable, we have the positive mass theorem, and that implies that the infimum of the Yamabe quotient is attained. So we just saw that if this fails, then the positive mass theorem can fail. And now we show that this also can fail. Okay, so we have a third theorem, theorem E. So this is still work with Cheng and Yang. Okay, so for S small, in fact, we have that the infimum of S3 J S theta 0 is equal to Y S3 J S3 theta 0. Okay, usually we have a strict inequality, but here we have equality, indeed, and YS3 JS theta 0 is not attained. Not attained. Okay, so this is one case in which you cannot minimize the Yamabe quotient. It's always possible to do it in the Riemannian case by the works of Aubin and Chen. Okay, it's always possible to do it if the dimension is greater or equal to 5. But in 3 dimensions, you can do it if the manifold is embeddable. Otherwise, we have counterexamples. So for the proof, maybe I'll just say a few words about the proof. So the proof uses a finite dimensional reduction. And there are maybe a couple of ingredients. So the first is that solutions, it's a classification result. So solutions of the Webster-Yamabe problem, so LB0 of U plus W theta 0 U equal to say W bar U cube on the standard sphere. So S3 J0 theta 0 are classified. Okay, so this is due to a result by Jason and Lee. I think it's 89. Let me check quickly. 88. I was wrong. 88. Okay, and so the solutions of the Webster-Yamabe problem on the standard sphere, they are classified. So I denote them by phi p lambda CR. So there is an explicit formula. But here, a point P is a point of the sphere, and lambda is a positive parameter. So when you look at them all together, so the set of the phi p lambdas CR, so when P and lambda vary, so they form a 4-dimensional ball. Okay, so they're parametrized by the ball. So this is the ball before, and the boundary is S3. Okay, why is that? Because so on S3, each phi lambda. So I want to explain why they form a 4-dimensional ball. Okay, on S3, the phi lambdas have this shape. Okay, they can be concentrated near some points, and the parameterization is essentially a choice of the center of mass of this distribution. Okay, so essentially you integrate on S3. So we have S3 that sits in F4. You take the function phi lambda to the 4, and multiply it by the position vector in R4 in the C. So when lambda goes to infinity, this converges. So when lambda goes to infinity, so this is converging weakly to a Dirac mass when lambda goes to infinity. It's converging to a Dirac mass at the point P. Okay, and therefore the weighted center of mass is converging to P when lambda goes to infinity. You can show that the constant identical equal to 1 is a solution, okay? And the center of mass will be at the origin. And when lambda varies, say, from 1 to infinity, then the center of mass is moving towards the boundary of the ball, okay? So that's why they form a four-dimensional ball, okay? So now what we do is that assuming, so this is to describe the family of all solutions of the Yamabe equation on the standard sphere. Okay, now we perturb the structure. So on S3 JS theta 0 for S close to 0. Okay, so suppose that that the infimum, so okay, that it is attained. So y of S3 JS theta 0 is attained. But you also know that the two structures are very close. Okay, so this will be close if S is close to 0 to y of S3 JS theta 0. So J0 theta 0. Okay, because the infimum vary continuously in S. Okay, so suppose that the infimum is attained by, say, US. So US is almost minimizer. So it's almost minimizing also the, say, Q theta with respect to the standard structure. Okay, so it's a minimizer. We're assuming it's a minimizer for the perturbed structure. The two infima are close, so US is almost minimizing the standard quotient. And therefore, you can prove that US must be close to, is actually equal to some function phi lambda PCR plus a little o1 in the Sobolev sense. Okay, it's almost minimizing the standard Yamabe quotient of the sphere, so it must be close to some of the minimizers. Okay, but on the other hand, you can prove that if you draw a picture, so by a Taylor expansion, if you expand the Yamabe quotient, so Q S theta of phi P lambda CR, okay, it actually goes up. It's actually higher than, maybe I should redraw the picture. Okay, so we have this property. So this is, let me do this. It goes like this. So you expand the quotient for the S structure on those standard solutions, okay? This limiting value, so when lambda goes to 0 and infinity, so this converges to y S3 J0 theta 0. But for S different than 0, different from 0, this is actually higher. Okay, so the energy is higher. And therefore, you show that if you are close to being minimal, the energy is always higher than the minimum on the standard sphere, and therefore the minimum cannot be attained. In fact, so minimizing sequences for y, or say qs, theta 0, will be of the type so one of those bubbles, phi lambda p CR, with lambda I going to plus infinity. Okay, you see, for minimizing this energy, it's convenient that lambda goes to either 0 or to plus infinity, which means that these functions are actually concentrated. Okay, it's a completely different picture. So if you draw the same picture on a Riemannian manifold, so this is QG of phi lambda. This is for MG Riemannian. The picture goes the other way. Okay, so this would be y Sn GSN, and when lambda goes to infinity, you approach it from below. Okay, we saw it from the expansion of Oban and Schoen. Okay, but this is going the other way around. Okay, so in the Riemannian case, minimizing sequences would tend to deconcentrate, so lambda gets smaller. In this case, for a minimizing sequence, lambda gets higher. So let me mention some open questions. So one is that we understood the mass for Rosse spheres, which are very special perturbations of the standard sphere. So they are nice and homogeneous. But one question is to understand the mass for general perturbations of S3 J S3 theta 0. And second will be to prove positivity of the mass in higher dimensions. And there are only some words when M, so some only some results in special cases for M to M plus 1 J theta locally spherical. Which is like locally conformally flat. So I can mention results by Cheng, Chiu, and Yang in 2014. So this is for n greater or equal to 3. And Cheng and Chiu in 22, n equal to 2 plus spin structure. Okay, so there was some question a few lectures ago about the developing map. So here in this paper, they use something like the developing map to prove such a result. Okay, here they need to use the Dirac equation. But for the rest, it's completely open. And we saw also the positivity of the mass is useful if you want to understand properties like compactness of solutions. Okay, existence is known, but so this could be useful to prove compactness. Is there any question? Okay, so let me discuss one last topic. So we don't understand the mass in general, but there is something which is a bit weaker that we understand in a little more detail. And let me discuss the so-called Einstein-Hilbert action. Okay, so the Einstein-Hilbert action is simply, I mean, more or less the integral of the scalar curvature. Okay, so we have, say, if we have a Riemannian manifold Mg, okay, so this action, so stripped R of G, so this is defined as the integral of the scalar curvature, but divided by the volume of M to the power n minus 2 over n. Sorry, n minus 2 over n, sorry. Okay, why do we divide by the volume? Because this quantity is actually scaling invariant. So if you multiply the metric by a constant factor, then everything is invariant. Okay, the interesting fact about this, it's actually an action, an energy, which also has interest in physics, in general relativity. But there is this fact that critical points of, So critical points of this action with respect to the metric are Einstein metrics. Okay. However, okay, I mean, this seems nice, but nobody can find the Einstein metrics using this variational characterization. Okay. So anyway, not practical. Or at least, well, nobody has been able to find Einstein metrics in this way. Also because so there are constraints to the existence of Einstein metrics. So you cannot put an Einstein metric on any manifold. Okay, on S1 cross S3, for example, there are no Einstein metrics. Okay, but in principle, if you can extremize this functional, you can find Einstein metrics. The other thing is that we have already seen this action. Okay, it turns out that so relation to the Yamabe quotient. Okay, so it turns out that if you choose a conformal metric, then QG of U coincides with the Einstein-Hilbert action of the conformal metric. Okay, so extremals of, say, conformal type are Yamabe metrics. So if you fix a conformal class of the metric and you consider critical points, you're going to find Yamabe metrics, metrics with constant curvature. If you vary also the conformal class, then you're going to find Einstein metrics. Okay, it's much stronger. Okay, so let's take the case of the round sphere, so Sn, GSN, which of course is Einstein. In fact, if you consider R of G, say R dot at the round metric, so the round metric is Einstein, so it is a stationary point of this action, but it has a saddle structure. So it goes like this. So this is GSN. Okay, so in the conformal directions, it's a minimum. But in the orthogonal directions, these are non-conformal. Okay, it's a maximum. I don't know whether the picture is clear, but if you move, if you do a conformal deformation, then it's a minimum, okay, the round metric. If you consider non-conformal deformations in this way, then it's a maximum. Okay, and this is strongly indefinite. In the sense that you have infinitely many positive and negative variations. Okay, so the second differential has infinitely many directions where it's positive definite, and infinitely many directions where it's negative definite. So that's why it's so hard to analyze such critical points. Okay, so let's consider now the analog, CR analog. Okay, so I call W theta the Webster curvature. So we are on a manifold M to M plus 1, J theta, okay? I call Q, which is 2n plus 2, is the homogeneous dimension. Because we saw that here the contact plane has dimension 2n. So 2n directions are just like the Euclidean, but the missing direction counts twice in homogeneity. Okay, so the homogeneous dimension is one more than the topological dimension. Okay, and we can consider the counterparts of the Einstein-Hilbert action, so which is Wj theta equal to the integral of W theta, and the volume form is theta wedge d theta to the n, divided by the volume, so the integral of theta wedge d theta to the n, to the power q plus 2, q minus 2 over q. Okay, it's a complete counterpart of the Riemannian one. Okay, where manifolds, assuming that this volume form never vanishes. Okay, so there is an assumption called the pseudo-convexity, which gives to this form a sense. So you can use it as a volume form. Okay, so we make that assumption, but it's quite standard. Okay, so we have this theorem. So theorem F. And before I go on, so let me recall the saddle structure on the Riemannian sphere. Okay, in the conformal directions, we have positive definite second variation. In the non-conformal direction, we have negative definite second variations. Now, in 3 dimensions, CR, we're going to see again a difference. Okay, so this is a paper from joint work with Claudia Feltra, former student of mine, Cheng, myself, and Yang. So 24 at the round sphere of dimension 2m plus 1. Theta 0. Okay, so the second variation of this CR, Einstein-Hilbert action. So it's positive definite. In the variations of theta, okay, in the conformal directions. And this was not really new. I mean, no big surprise. And then there is a difference when you write J, so which is like a change in the conformal structure. So for n greater or equal to 2, the second variation in J is negative definite. Okay, just like the Riemannian case. But things are changing in dimension 1. So for n equal to 1, the second variation in J is negative definite. On embeddable variations. Okay, so negative definite on embeddable variations, which are the ones that behave like the Riemannian case. So when we have the positive mass theorem, but on the non-embeddable ones, it's positive definite. So n positive definite in the orthogonal ones. And so we used crucially some work by John Bland in 1994. So he studied, so he understood the say the tangency condition to embeddability via Fourier analysis, say on S3, J0 theta 0. So he varied the CR structure J, okay, and he understood which variations are infinitesimally embeddable via some Fourier analysis. In J somehow. Okay, so he made J0 vary. So J0 goes into some J, and he understood somehow in Fourier modes which are the deformations that infinitesimally preserve the embeddability. So we did an expansion of the Einstein-Hilbert action and verify that, surprisingly, those Fourier modes that give you embeddability also give you a nice second variation negative in the variation of J, And otherwise, in the orthogonal variations, the sign is different. Okay, so with this, I would like to conclude, and I'm open to any question.
Professor, this Panit's operator P that you defined today,
yes.
For these Rose spaces, even if you change S, this is going to remain the same, right? Because it's depending only on theta?
No, in fact, it depends on I didn't write the lower quantity, I mean, the lower order terms.
Okay.
Where is that? I lost it. Okay, here. Okay, so these lower order terms, okay, first of all, this also depends on S. Okay, because, okay, I've been a little rough, so there is some dependency in S also here, but these lower order terms involve the so-called torsion. So for a Riemannian matrix with the Levi-Civita connection, the torsion is always 0. But it's not true in general for CR manifolds. So this torsion is sort of lower order, and it depends on S. So since it turns out that the Rossi spheres are not embeddable, and in fact, the Panit's operator is not a positive definite.
So they need not be positive definite for the other S.
Exactly. Because if the Panit's operator is positive, we have a positivity of the mass. But here the mass is negative, so the Panit's operator cannot be positive.
And maybe just another doubt. Like, so I was just curious about like whether the spectrum of this this operator is going to be helpful, like being positive definite. Is it being used somewhere? Or? Like
we use it in a formula of integration by parts. So we have, so we can write the mass. By the way, I can share if the organizers or if the audience is interested, I can share some handwritten notes that I have. So I don't know, maybe it's better if I write, if I show this formula. But here we have the mass appearing in this formula. And we write it as a sum of some squares. And then in one of the terms, there is also the Panit's operator appearing. Okay, so we write the mass as a sum of positive terms plus some term that involves the Panit's operator. If the Panit's operator is positive definite, that other term is also positive.
Okay. Yeah. Thank you very much. Thank you.
So I can share the notes, so there are a little more details compared to what I discussed.
Anything is known about the compactness?
Sorry, I didn't hear you.
Yeah, anything is known about compactness?
Oh, there are some, in fact, okay, this student of mine, Feltra, pushed, so we saw that if embeddability fails, okay, so if embeddability fails, that's a very good question. Positive mass theorem can fail. This can also fail, so being able to minimize the Yamabe quotient. It turns out that, okay, in low dimension for the Riemannian case, the Yamabe equation is compact. It's compact until 24. But there are, for the CR case, non-embeddable examples where the Yamabe problem is not compact. So he has been able to exploit the non-embeddability to construct blowing up sequences on non-embeddable manifolds. Yeah, it's a very good question.
Any other questions? Okay, though there are no other questions, so let's thank Professor Andrea Malchiodi
for
a beautiful series of lectures covering various topics on Yamabe.
I was very happy, so thanks for attending and also for the many interesting questions I got. So as I said, I'm happy to share my notes if you think they could be useful.
Yeah, we will contact you. Yeah.
Okay, thank you very much.
Yeah, thank you.
Okay, bye.